Babu Addepalli, and then participants, everyone. Welcome to the day 5 of this one week online FDP on antennas for 5G communication and beyond. And today's session is a 5G sub 6 gigahertz antenna design. It is a hands-on experience. Okay, right. So I'm delighted to introduce today's resource person, Dr. Tata Babu Addepalli. He was born in Andhra Pradesh, India. He received his BTech degree from JNTU Hyderabad in 2007 and his MTech degree from JNTU Kakinada in 2010 and his PhD degree from JNTU Anantapur in 2022. Currently, he is working as an associate professor in the Department of Electronics and Communication Engineering at Aditya Engineering College, Surampalem. He has published 18 SCIE papers, 4 Scopus Index papers, and 8 papers presented in international conferences. The papers are published in various reputed international journals like IEEE Access, Alexandria Engineering Journal, elsewhere, International Journal of Communication Systems, Willy, Transaction and Emerging Telecommunication Technologies, Willy, Electronics from MDPI, Wireless Personal Communication, Springer, Wireless Networks, Springer, Journal of Electromagnetic Waves and Applications, Taylor and Francis, and IETE Journal of Research, Taylor and Francis. Presented 8 papers in conferences, 7 from IEEE Explore and 1 is from Springer. Published 2 book chapters on terahertz antennas and planar microstrip antennas and published 2 patents also. He attended more than 40 workshops related to antennas and wireless communications in various reputed institutions. He is a reviewer for the reputed journals like IJCS, PIER, Electronics, Telecommunication Systems, AEU, and so on. His research areas of interest are microstrip patch antennas, MIMO antennas, 5G antennas, sub 6 GHz and wave, UWB antennas, flexible antennas, characteristic mode analysis, terahertz antennas, and metamaterial antennas. Right, sir. Thank you, sir, and welcome to the today's session, day 5 on 5G sub 6 GHz antenna design. So I request Dr. Tata Babu Addepalli sir to continue his session.
Yeah, thank you, sir. Thank you for introduction about me. Sir, are you hearing me?
Yeah, can.
Thank you. Thank you, Vishnuvardhan Reddy, sir, regarding introduction about me. And good morning to everyone, conveners of the program and coordinators of the program and committee members of the program. A very good morning to everyone and a very good morning to participants who are joined now. And first of all, I would like to thank to the management and principal, sir, to support and motivate the department to organize these type of events for faculty. Then I thank to HODs of EC department, Radha madam and Satyanan sir. So far 4 days gone, 4 different people, they deliver good lectures. And yesterday CST, today my session on particularly 5G sub-6 GHz application using HFSS hands-on session. So as usual, we have 2 sessions. In the first session, I want to tell some introduction about 5G with MIMO. In the second session, I want to tell the hands-on session how to design the 5G antennas using HFSS. Right? Shall I share my screen?
Yes, sir.
Sir, is my screen visible?
Yes, sir. It is visible.
So before start the session, I want to introduce myself a few seconds. Myself, Dr. Tata Babu Addepalli. I am from Guntur, AP itself. Currently, I am working here as Associate Professor Department of EC College, Aditya Engineering College. My PhD from JN2 Anantapur 2022 on MIMO antennas, particularly UW applications. This is my PhD details. Now coming to session 1. Welcome to the participants. A 1 week online FDP on antennas for 5G communications and beyond. So in this session, I want to give you some brief introduction about importance of 5G antennas in the current society, in current wireless communication systems, how it give maximum data rate, I will explain you. So when coming to antennas, what is the need of antenna in wireless communication? So depending upon mode of propagation, that means the signal is transmitting from source to destination. We have two types of communications. One is wire communication, another one is wireless communication. In wire communication, we are sending the information with the help of wires, but in wireless communication, information sending with the help of antennas. So in wire communication, there is a physical link between source and destination. In wireless communication, there is no physical connection. So with the help of antennas only, we can send the signal from source to destination. In that, the information is in the form of electromagnetic wave, electric field and magnetic field. These two are always perpendicular to each other. That's why the term antenna came into the wireless communication. Means without antenna, there is no wireless communication. So here, what is an antenna? So generally, antenna means it is a radiating element. According to IEEE standard, antenna means it is a radiating or receiving electromagnetic waves. Generally, it is a metallic structure, whatever the metallic rod or metallic copper, any material, metallic structure, it produces electromagnetic waves and receives the electromagnets from the other end. So when we comes to the antenna, so if you think about the antenna, two types of antennas comes in our mind. One is parabolic dish antenna here, and another one is in olden days we are seeing in every buildings Yagi wood antenna. So this is the parabolic dish antenna, and this one is Yagi wood antenna. These two are high directional antennas because of these are providing high directivity. Depending upon structure constructed, these are the purpose of these antennas is broadcasting purpose. So this is the antenna. So generally we are seeing nowadays so many antennas, microstrip patch antennas and sectoral antennas, some different shapes of antennas, lens antennas. Right, these are all are antennas. They all are radiating electromagnetic waves and receiving the radio waves. Now, so coming to what is antenna array? Array means a group of elements connected side by side. Here, that means a set of multiple connected antennas. So previously we have seen single antenna. Antenna is a radiating element. It radiates and receives the electromagnetic waves. But here antenna array means same antennas are connected side by side with some distance. That is called array. Number of antennas connected side by side. Simply say that. What is the importance and what is the objective of number of antennas connected side by side is the main objective or the main advantage of antenna array is to improve the directivity so that the gain will improve. You can see here, if you take this one is one antenna, this is simply a single antenna. Here, more number of antennas connected side by side. Here, 1, 2, 3, 4, 5, 6, 7, and 8. 8 antennas are connected. This is an array. Number of antennas connected side by side. So the purpose of this array is to improve the directivity so that the gain will improve. Here, you can see in this figure also, number of patches are connected side by side on the substrate. So this one will produce maximum gain here, maximum gain. So first of all, the directivity will improve, then automatically the gain will improve. So it produces the maximum gain and maximum directivity. How it will gives the maximum directivity and a maximum gain, I will show. Yeah. So this is the main advantage of antenna arrays. It improves the directivity and automatically the gain will improve according to G equal to KD. So from this figure, we can see this is the single radiating element. You can see this is the radiation pattern of a single element antenna. Here, this is the two radiating element. This is the two element array. So this is the radiation pattern. This is the four element array. This is the radiation pattern. If you observe the radiation patterns of three cases, so this is the radiation pattern, just like half circle. If you see this one is elliptical structure with low axial ratio, and here this is the more directivity compared to this one. How it will get? more directivity means first we should know the what is directivity and what is gain and what is K. That K means antenna efficiency. Uh, just imagine in antenna array, number of antennas connected side by means one antenna is radiating parallelly, second antenna is also radiating. If you connect both, then the radiation of both antennas will combine. The resultant is more gain. Then automatically the main lobe is definitely large. Then automatically the directivity will improve. So if we add one more antenna there, that is also radiating. So three radiation patterns are combined. It gives more directivity and it gives more a major lobe which is high. So if you add one more, or if you add one more, if you add one more, all the radiation patterns are combined, it will give more directivity, then automatically again will improve. Now, what is directivity? How it is in this figure, this is the directivity high. How we say this directivity is high and this one is somewhat less compared to this one. This one is somewhat less compared to this one. How you say directivity is less? So what is directivity? Generally, we can say that directivity means it is the ratio of maximum radiation intensity in particular direction to the average radiation intensity. Maximum radiation intensity to the average. For example, if you take isotropic antenna means it is an ideal antenna, not the practical antenna. It is a hypothetical antenna. It produces electromagnetic waves equally in all directions. It produces electromagnetic waves in all directions equally, just like a cork ball. If you see the cork ball, it is the round shape. If you place one antenna inside the cork ball, it produces equal radiation in all directions. So if you want to calculate the directivity, if you take one cork ball, just imagine the one cork ball, the outer is entire the fields. If you want to measure the directivity at this point, suppose the field strength is 5, right? So here the field strength is 5, here the field strength is 5, here the field strength is 5 because it is isotropic antenna. So it radiates equally in all directions. If you want to measure the directivity of that antenna, maximum radiation, if you take in this direction, if you take maximum, suppose it is 5 by, if you take 10 points. So 5, 5, 5, 5, 5, all directions 5s are there. If you take only for 10 points, 5 by maximum radiation intensity in particular direction, 5 by average. Average means if you take 10 points, 5 plus 5 plus 5 plus plus up to 10 times by average means 10. 5 plus 5 plus all the 5 means 50 by 10, that is 5. Already numerator is 5. So 5 by 5 1 is 1. That's why the directivity of isotropic antenna is 1. Now, coming to this picture, this is not isotropic antenna, this is the half circle, and this is not a isotropic antenna, this is not isotropic antenna. Now this is the maximum direction and remaining direction is very small, very low. So what is the directivity? It is the ratio of maximum radiation intensity.
Sorry for the interruption. The slides are not visible. Yes, now visible, sir.
No, okay. So compare these three figures. We know the directivity of isotropic antenna is 1. Already we discussed. So here the radiation pattern is not isotropic, and here this is not isotropic, and it is not isotropic. So here, if you calculate directivity here, the maximum radiation intensity in this direction and remaining direction is very small. So what is the directivity maximum to the average? So maximum, the numerator term is high, the average is small, then automatically the directivity will improve. That's why one of the objective of antenna is directivity will improve, then automatic gain will improve. What is gain? So G equal to KD. So what is K and what is G? G here, G means gain of antenna. So generally, most of the people, they think about gain means in electronic circuits, gain means output to the input. Suppose voltage gain, output voltage to the input voltage, current gain, output current to the input current, power gain, output power to the input power. But in antennas, it is different. So gain means the ability of antenna to radiate the radiation in particular direction with respect to the isotropic antenna. That is the meaning of gain of antenna in antennas. That is not same as in electronic circuits. The ability of antenna radiates radiation in particular direction with respect to that particular direction, any direction with respect to isotropic. We have to measure the radiation with respect to isotropic. So already I told you, isotropic antenna is a hypothetical antenna. No antenna that generates equal in all directions. It is a hypothetical antenna. It is an ideal antenna. But if you want to measure the gain, we have to compare with isotropic antenna. That's why we can see in most of the papers, gain versus frequency graph, gain in terms of dBi, not dB. We have to put dBi with respect to isotropic. So that is the meaning of gain. And now coming to K, that K is antenna efficiency or total efficiency. So here efficiency of antenna is defined as, for example, if you take one antenna, I am applying 1 watt of power here. That is 1 watt of power. That means 1000 milliwatts I am applying here. So based on impedance matching between the port and power source. Here, this is the feed point. It has some characteristic impedance. And if you add one more component here, then overall characteristic impedance will change. Now, if you take here, the impedance here is there, some source is connected here. If the matching is there, impedance matching is there, the total power is accepted. If there's some little bit deviations are there, some part of power is reflected back. So initially, some input power is applied. That is called input power or applied power. Some signal due to mismatch between the source and feed point, some part is reflected back. So that is called reflected power. Remaining power is accepted by the antenna, that is the accepted power. Then that accepts the antenna that send into the free space. Then radiation efficiency means here input power is there, reflected power is there, accepted power is there, radiated power is there. Now radiation efficiency is defined as it is the ratio of radiated power to the input power. Radiated power to the input, that is called radiation efficiency. Here we have defined the two terms. Total efficiency is there and radiation efficiency there. Antenna efficiency or total efficiency, and the one more term is radiation efficiency. So here I am applying 1000 milliwatts. So due to mismatch, only 50 milliwatts is reflected back. That is the reflected power. 950 milliwatts is accepted. If the 950 milliwatts is directly sent into the free space, if you not consider the losses in the antenna, that losses may be either conducting losses or dielectric losses. If you not consider the losses in the antenna, it is called radiated power to the incident power. That is the radiation efficiency. If you consider the losses in the antenna, that is the conducting losses and dielectric losses, that means so 1 watt is applied, 50 is reflected, 950 is accepted. Suppose one more 50 milliwatts is losses in the antenna, 900 milliwatts is sent into the free space. So their rated power is 900. So previously 950, now it is 900. So that 900 by 1 watt is radiation efficiency, total efficiency. So 950 by 1000 is radiation efficiency. So 950, no consideration of losses in the antenna. If you consider the losses in the antenna, that is called total efficiency or antenna efficiency. So that's why the input power is 1000 milliwatts, the output power is either 900 or 950. That's why the efficiency is always less than 1. So the main objective of antenna array is to improve the directivity, then automatically gain will improve. Now coming to MIMO. So MIMO means multiple input, multiple output. So it is an application of an array. Here also number of antennas are there, but the objective is different. So the objective of MIMO antenna is to data higher improve. It improves the data rate, channel capacity will improve, quality of service and reliability. How it will improve? So here, in case of you can see here, single transmitter and single receiver. Here single antenna is there. This is the single input, single output. This is the single inputs. This is the multiple output. Two antennas are there. So here we show multiple input, single output. Two antennas here. One antenna is here, and this one is multiple input, multiple output. The objective of array is to improve the directivity and to improve the gain. And here the objective is higher data rates, higher channel capacity, quality of service, and reliability. How it will improve, and what is the difference between array and MIMO? So in MIMO, I will explain. Yeah. So in traditional communication system, I will tell you what is the difference. Next slide. In traditional communication system, usually we are using single antenna at the transmitting end, single antenna at the receiving end. So here this is the single antenna is here. This is the single antenna at the output side. This is a single input, single output system is there. So here the capacity of the channel is very limited because only one antenna is here. According to Shannon channel capacity theorem, the channel capacity C is equal to the bandwidth V into log 2 1 plus signal to noise ratio bits per second per H. So channel capacity is directly proportional to the bandwidth and signal to noise ratio, signal power to the noise power. So that means it is channel capacity depends upon either increasing the bandwidth of the channel or either increasing the either increasing the power of the signal, signal power to the noise power. So here nowadays all the systems are very portable and compactness because of some constraints in the portable devices. If you increase the signal power, then if you increase signal power, the battery will damage in the portable devices. So beyond that some power level, we cannot increase the signal power. Then alternative sources increase the channel bandwidth. Because nowadays all the devices are portable and very compact structures. That's why we have no right to we have no chance to.
Sir, you are muted. Hello? Sir, please unmute your mic. Okay, right.
Now it is okay, sir.
Right, okay.
Yeah. So in 1990s, the MIMO system is proposed by Aragisri Palras. How to increase? Are you hearing me? Are you hearing me?
Yes, sir. Yeah.
Yeah, here I want to explain some details. So channel capacity here C is equal to B into log 2 1 plus signal ratio. There is a constraint in the signal power improvement. So another way is bandwidth. For example, if you take Bluetooth 2.4 to 2.480, very narrow bandwidth. So then the channel capacity is less. And the second one is if you take WiMAX. WiMAX is 3.4 to 3.7. The bandwidth is 0.4 gigahertz. Then the somewhat the channel capacity will improve. If you take WLAN 5.15 to 5.85, and here it is a 0.7 gigahertz, then the bandwidth will improve. The channel capacity will improve. Now, if you take the UWB antenna in 2002, FCC announced these are all unlicensed bands. Everyone you can use their commercial purpose. Bluetooth, WLAN, WiMAX, all the bands. If you take UWB ultra wideband region, that is 3.1 to 10.6, it is a huge band. In 2002, FCC, Federal Communication Commission, they announced a huge band for commercial applications. Everyone can use for commercial applications. That is, band is from 3.1 to 10.6. Then automatically here, that is nearly 7.5 gigahertz bandwidth, the channel capacity will improve. And again, even if you increase the channel capacity in this UWB technology, there is a main problem in UWB technology is multi-path fading, because it is useful for only indoor applications. For short distance communication, mostly 10 meters, less than 10 meters, like system to mouse connection, wireless connection, system to speaker connection. If you want to detect the person inside the wall, by using UWB technology, we can identify it. But it is very small distance communication for identification the signals or whatever. So here the channel capacity is high even, but it is suffering with one problem that is called multi-path fading. That multi-path fading is overcome by a new technology came into wireless communication that is called MIMO, multiple input, multiple output. So initially the idea was given by the Aragisri Palras. Later it is mathematically proved by pioneer Foshni in 1998. According to Foshni, the channel capacity is derived. The channel capacity C is equal to log 2 det IN. The N indicates the number of receiving antennas. This is the identity matrix. That rho indicates the signal to noise ratio, signal power to the noise power. M indicates the number of transmitting antennas. Here H indicates the channel coefficient matrix bits per second per H. So how it will improve, we have to analyze. Here we have to think if you take CISO system, single input, single output system, the channel capacity according to Sharon Fano, that depends upon depends upon the bandwidth because of constraints in the power also there, and here also there same because of all the devices are portable. Here, if you take the CISO system ISO, suppose it will send 1 bit per second per H. If you take MIMO system, R bits per second per H. That R indicates rank of the channel coefficient matrix. This is the rank of the channel coefficient matrix. Then automatically the data rate will improve, then the channel capacity will improve. So that is in the MIMO system, it improves the high data rate. Nowadays, all are using MIMO antennas in the mobile phones and broadcasting purpose. Number of antennas are connecting to get the more data rate and more channel capacity and to get the quality of service. Here you can see a MIMO system, how MIMO system is connected. This is the transmitter and this is the receiver. A transmitting antenna 1, 2, 3, up to m number of transmitting antennas at the receiver side and number of transmitting antennas. And here, this is the antenna 1 here, H11, this 1 for H21, this 1 indicates, this is the antenna 1 for the transmitting and this 2 indicates received by the antenna 2 at the receiver side. That's why it is the H21. H1 it is connected to transmitting antenna 1 is connected to all the antennas at the receiver side. 2 is connected to all the antennas at the receiver side. Like that, nth antenna is also connected to all the antennas at the receiver side. This is called diversity performance. Due to this, the channel capacity will improve. How it will improve? Next slide I will explain. And it gives the quality of service. I will show the figure how it improves the quality of service. So here, based on these connections, we can define the channel coefficient matrix. So based on these values, so we have to calculate the rank of the matrix. Based on the rank, we can define the how much amount of data rate will improve, how much capacity will improve. That is R into number of bits per second. Already I told you, in case of single input, single output, it is 1 bit per second per H. In case of MIMO systems, R bits per second per H. That R indicates number of that is the rank of matrix. Yeah. So how it will improve the data rate here? We can explain. So basically, two types of signal techniques we are using in the MIMO systems. One is space division multiplexing or spatial multiplexing, and another one is space-time coding. In the space division multiplexing, suppose I have a data 1010101001. That is the transmitting. This is the original message. So in case of 2-element MIMO antenna, so transmitting antenna 1, transmitting antenna 2, 101. So different techniques we can use, QPSK, even number of bits or odd number of bits, whatever the technique you are using the transmitting section, those bits are given to the transmitting antenna 1 and another bits are given to transmitting antenna 2. It is sent to antenna 1 and it is sent to antenna 2. And similarly, this is sent to antenna 1, it is sent to antenna 2. That means in case of a single antenna system, first 110 sending and it is received by the antenna 1, and next one is 001 sending, it is received by the antenna second case. That is in case of single input, single output. Here parallel we are sending 110 and 001. That definitely the data rate will improve number of bits per second. So previously if you take 110 3 bits per second, now if you take 2 antennas 6 bits per second per head shape we can measure. So that by using space division multiplexing, we can increase the data rate so that the channel capacity will improve. So based on this one, you can calculate easily. If you increase the number of antennas, then automatically data rate will improve, the channel capacity will improve. So here the channel capacity depends upon number of antennas at the same time, multipath environment values. Because of we have to calculate the rank of the channel coefficient matrix. This is the space division multiplexing. And another technique is space-time coding. So this is the original message, same information 101001 that is given to transmitting antenna. That means the same information is given to all the antennas of the transmitting section, that is sending to receiving sites. So here transmitting antenna sending to 1 and 2 of receiver side, and 2 is sending to 1 and 2 of receiver side. So that if any one of the link is disconnected due to the fading in the multipath environment, definitely one of the signals is received by the receiving antenna. Some signal processing takes place here, then finally automatic. Definitely we can receive the original message because multiple times the signal is sending, so that the quality of service will improve and reliability will more, because definitely you can receive the any one of the path the signal. That's why one of the one more objective of MIMO system is it gives highly reliability. That means definitely you can receive the signal from the transmitting side. And quality of service. Definitely sometimes the signal will damage due to the obstacles in the obstacles between the transmitter and receiver. One more signal, there is no obstacles between the transmitter and receiver. So the signal we can receive. So better signal we can take, then the quality of service will improve. Next, advantages. High data rates, improved channel capacity, and improved diversity gain, highly reliability, high quality. These are the main advantages and objectives of MIMO system. Yeah. So coming to limitations of MIMO system, what is the main limitations? So previously I said, what is the difference between array and MIMO? In array, number of antennas connected side by side with some distance. There, the radiations of all the antennas are the combined, it produces more directivity, then so automatically the gain is increasing. But here, the main limiting factor when number of antennas connected side by side, the information contained. So here, the information contained in the transmitting antenna one and this one is a different. If you combine these two, then automatically the information these two will change. This is the main limiting factor in the MIMO system. That means if you take a portable devices, number of antennas are there. So number of antennas are there. So here mutual coupling. So antenna one is there, antenna two is there. Suppose it is radiating like this and another antenna radiating is like this. So there is a collision between two radiations, then that is called as a mutual coupling. Due to mutual coupling, the information contained in the signal will disturb. So that is the main limiting factor in the MIMO system. That means in array, the radiations should be combined so that the gain and the directivity gain will improve. But if we combine here, it is a problem in the MIMO system. That's why these two should be isolated. That is the main difference in array antennas and MIMO antennas. If here we combine the signal, the information damaged in the antennas, then we cannot receive the signals exactly at the receiver side. So that we have to improve the isolation and we have to decrease the mutual coupling between the antenna elements. I think you understand about what is the importance of array and what is the importance of MIMO system. There, in array, the radiation should be added so that the gain will improve. Here, it should be isolated. Otherwise, the information contained in the individual antennas will change. How? What are the major factors influence on the mutual coupling is one is surface currents and another one is surface waves and the third one is free space radiation. Now, if you take one antenna, surface currents always flowing on the conducting materials. If you take microstrip patch, it consists of three parts: the top layer and the bottom layer. In between substrate is there. The top layer is conductor, the bottom layer is conductor, the middle one is substrate. That is the dielectric medium. The surface currents is always flowing on the top layer and bottom. That means conducting materials. And the second one is the surface waves. That surface waves always flowing on the common dielectric medium. Because if you take one substrate here, antenna one is here, antenna two is here, antenna three is here. All are connected in the common substrate. The surface waves are flowing in the common substrate. So due to the surface waves flowing from one antenna and another antenna two, there is a chance to coupling between the antenna elements. And the third one is free space radiation. Antenna one is here, antenna two is here. The antenna one radiation will be like this, antenna two radiation will be like this. This is the radiation. There is a collision between the two radiations, or there is interaction between the radiations here. Then automatically mutual coupling is introduced so that the information contained in the individual antenna elements will change. Then we cannot retrieve the original message signal at the receiver side. So these are the main parameters. The factors influence the mutual coupling between the antenna elements. One is surface currents. The second one is surface waves, and the third one is free space radiations. And in general, S parameters. In general, S parameters in 2-element MIMO antenna. So what is the minimum value is acceptable in practical application of the designing the MIMO antenna S21? That is the transmission coefficient. It should be less than 15 dB. If you define S21. In case of mutual coupling, it is minus 15 dB. If you want to define S21 as isolation, it is plus 15 dB. So whatever, it should be less than 15 dB. Isolation should be high. Now, correlation. So correlation means that is the interaction between the two radiations of the two antennas. High correlation between the signals in MIMO antennas and antennas are connected side by side. Already said. So due to correlation between the two antennas, the signal performance will degrade. The overall the system performance will reduces. It is due to the high mutual coupling between the antenna elements. So in general, envelope correlation coefficient, this is the one of the important parameter, particularly MIMO parameter. MIMO parameters. So we have different MIMO parameters are there. ECC, envelope correlation coefficient, diversity gain. Diversity gain, it is different from directive gain. Directive gain or directivity, that is different. That is the antenna parameter. And the diversity gain, that is the MIMO parameter. It is also antenna, but it is a diversity gain means it is a MIMO parameter. And mean effective gain and torque, total active reflection coefficient, and CCL, channel CCL. These are the parameters we have to define. So for a two element antenna system, the ECC is given by ECC is equal to S11, S11, S12, S21, S22, like that. So this is the expression for ECC. The acceptable value of ECC is ECC is 0.5. So ECC defines the correlation between the two antenna elements in the MIMO system. So effects of mutual coupling. So if there is a more mutual coupling between the antenna elements in the MIMO system, it reduces the radiation efficiency. Already we discussed about radiation efficiency due to impedance mismatching and deviations in the antenna radiation, decrease the channel capacity. How it will affects? So here you can see antenna M is here, antenna N is here. Antenna 1 is M is here, antenna N is here. Suppose antenna 1 is radiating, it radiates in all directions, and antenna 2 is here. Both are connected in the common substrate. What will happen? We can see here. So here 0, it is radiating. Then some part of radiation excites the beside antenna, so that the self impedance and the mutual impedance of the antenna M will change. Similar, at the same time, antenna 2 is radiating, some part of energy is disturbed the second antenna radiation pattern, then the self impedance and the mutual impedance of this antenna N will change. So due to that, the self impedances of both the antennas and the mutual impedance of both the antennas will change. Due to changes means the surface currents flowing on the both antennas will change. Surface current antennas will change means impedance mismatch. That means the operating frequency will deviate. And then so this radiation affects this one, and this radiation affects this one means the radiation pattern of this one is disturbed. That's why the radiation pattern will deviate, and so that finally the channel capacity will reduce. So this is the same concept we can explain in torque also. Total active reflection coefficient. Yeah. So how can you? So mutual coupling reduction techniques. The flow of surface currents can be diverted or blocked or attenuated by the employing decoupling structures. So far, so different decoupling structures are there. That means how to reduce the mutual coupling between the antenna elements in the MIMO system, or how to increase the isolation between the antenna elements in the MIMO system. Defected ground structures. So this is the one of the technique by removing some part of ground from the whole ground. That part remove may be either periodic structures or non-periodical structures. And the second one is polarization diversity. That means if you take a 4-element antenna, so if you place 4 antennas, one antenna is in this direction, another antenna is one antenna in this direction, another in this direction, another in this direction. So all are perpendicular to each other. Then the polarization diversity means one antenna is horizontal polarized, another one is vertical polarized, and again another one is horizontal, another one is vertical. If you place four antennas in square shape, that is the polarization diversity. By using the technique, we can increase the isolation. And another one is electromagnetic band gap structures. A periodical arrangement of strips are placed on the ground plane or top plane or in between the substrate. That is electromagnetic band gap structure. So proper arrangement of EBG structure, so we can enhance the isolation between the antenna elements. And the fourth one is by placing parasitic elements between the antenna elements. When two antennas here, so the radiations are affecting antenna 1 and antenna 2. By placing parasitic elements between the two elements, we can increase by using metametric structures to cancel out the surface currents from one antenna to another antenna by using metametric structures. And another one is by using neutralization techniques also, we can increase the isolation between the antenna elements. So both the terms same. Increase the isolation or decrease the mutual couplings, both are same. That is the main limiting factor. Main limiting factor in the MIMO systems is mutual coupling. Now, so 5G. So we know 1G, 2G, 3G, 4G, and 5G. In 1980s, 1G technology, 91, 2G, 3G, 4G, we know. It is a 5G technology. It is the essential technique required for the 5G evolution is MIMO technology. So partial deployment in the 3G technology at the end of 3G. So complete deployment in the 4G technology. So 4G LTE bands, it is complete depends upon MIMO technology. So 5th G technology also MIMO technology is required. So to what is the need to improve the channel capacity, to improve the data rate? The main intensity is work is to improvement 1G to 2G, 2G to 3G, 3G to 4G, 4G to 5G. So in 3G, this is the speed 2 Mbps. In 4G, 1 gigabits. In 5G, the speed is 10 gigabits per second. We can see the latency. So here 1 second, this is the 300 to 1000. So finally, in case of 5G, the latency is 1 millisecond. So before that, it is 50 millisecond. Latency means time for sending information from source to sending from source to destination. That is the time. Sending to receiving time. Now, here 4G and 5G. Here 4G LTE bands are there. So 3G bands are there, and here 5G bands are there. 2G bands are there. So initially 800 megahertz bands are there. 2G 900 and 1800 megahertz bands are there. 3G 2.1 gigahertz bands are there. In LTE bands 10 to 12 for cellular applications. 10 to 12 LTE bands are there. And here in 5G, there are three types of bands are assigned by the ITU. One is lower 5G, and another one is sub 6 5G, and the third one is millimeter 5G. You can see here, this is the C band 3 gigahertz to 5 gigahertz. These are sub 6 5 gigahertz 5G for cellular applications. Another one is millimeter 30 gigahertz to 300. And other than this, one more 5G is there. That is the lower 5G, which is less than 1 gigahertz. That is around 600 megahertz. So here one more thing. So how the data rate improve generation to generation means. So in 2G, the carrier bandwidth is 200 kilohertz only. In case of 3G, the carrier bandwidth is 5 megahertz. And here the carrier bandwidth is 10 megahertz. Here the carrier bandwidth is 20 megahertz. We can observe here the carrier bandwidth is increasing at the same time from 4G onwards. We are using MIMO technology, then automatically speed will increasing. That's why the speed is 10 gigabits per second. So that is the main key point in the how to improve the channel capacity and data rate in the 4G and 5G because of carrier bandwidth is high. Up to in 1G and 2G there is a circuit switching. In 3G for some of them circuit switching and some of them is a packet switching. For voice calls it is a circuit switching. For data it is packet switching. From 4G onwards the data transmission is packet switching. That's why previous slide I have shown in 1010 like that. Now, so you can see one funny figure, right? How to improve the 1G to 3G. So just like one figure I have taken from the Google. I think most of these people seen in the Google, monkey to man. So here 1G, 2G, 3G, 4G, how to implement. So now 1G, 2G, 3G, 4G, 5G, and now coming to 6G, the speed will definitely increase. We can see at the time of 2030, the more data rate, we can expect a number of times greater than the 5G technology. Currently, it is the work is going on with ITU. Now, coming to 5G technology, already I said three types of three categories in the 5G. One is lower 5G and sub-6 5G. Here, this is the sub-6 5G, and this is the millimeter wave. So here, three bands are there particularly defined: N77, N78, and N79. And now, new radio 77, 78, and 79. So 77 is 3.32, 4.2. And N78 3.3 to 3.8 and 4.4 to 5.5. See, this is the sub-6 gigahertz for cellular applications, and a millimeter wave here N57, N58, and N260. Sorry, N258, 257, 261, 260, like that in future 47 to 87 that come into the wireless technology. Our intention is design of 5G antennas, particular MIMO 5G antennas, sub-6 gigahertz. In the next section, we will see. Yeah. So how it improves the 1G to 2G, 1G, 2G, 3G, 4G, and it is a 5G. So everyone will know our mobile has multiple number of antennas. Wi-Fi antenna is there, and WLAN antenna is there, and for Bluetooth applications is there. And if it is 3G mobile, 3G antenna is there. If it is 4G, 4G antenna is there. If it is 5G, 5G antennas are there. Suppose your mobile is suitable for all the generation antennas, means that is built up with all the antennas. 1G antenna 900 megahertz, 800 megahertz, 2.1 gigahertz, and LT bands, and 5G means N77 or N78 or N79. All the antennas were built on your mobile, because your phone is a 5G mobile. Now, coming to microstrip patch antenna, this is the diametric view. If you want to design the microstrip patch antenna, we should know the three parts. So already I told that is the top layer is there, and this is the bottom layer. In between substrate is there. So three parts are there. Top layer is radiating patch. The bottom layer is ground. In between dielectric medium. It is a substrate. It has some dielectric constant epsilon r. This is called relative permittivity, and this is the height of the substrate, and this one is the length of the patch, and this is the width of the patch. So these two are conducting materials. The middle one is dielectric medium. It is substrate. Why you are choosing microstrip patch antennas? Because it has more advantages compared to all others, particularly depending upon application point of view. Suppose for broadcasting, for long distance communication, we are using parabolic dish antennas, agate antennas. But if you want to take some portable devices, and we need a compact structures, that's why we have to go for patch antennas. So if you increase the directivity, parabolic dish antenna, it provides the high directional patterns and high directivity. How we can increase the more directivity using a microstrip patch antenna is by placing a number of antennas, number of patch elements connected side by side, so that the directivity will improve. It covers the largest region. So that is the one way to get the more directivity. So here I want to tell advantage of only microstrip patch antenna. So it is a compact structures, no simple planar structures. It is a lightweight because of low profile. It is a small size. It can suitable for conformal structures and easy of fabrication, low fabrication cost. This cost depends upon the what type of substrate we are using for fabrication. More robust, easily integrated with PCB boards because of compactness, and offers wide bandwidths and stable radiation patterns. Stable radiation pattern means if you suppose if one antenna is operating particular band, in the entire band the radiation pattern should be stable. Yeah. So antenna is perfectly working or not? Is it suitable for applications or not? So the main key point, the hot key point of the antenna is we have to define the reflection coefficient. Reflection coefficient. It defines the how much amount of power is reflected back towards the source from the antenna. Now, so from the figure, you can say some source is there, load is there, forward power is there, reflected power is there, some load is there, and here it has some characteristic impedance, or ZL is there, load impedance, Z0 is characteristic impedance. So we can define here according to the equation. Now, I want to tell you reflection coefficient. If you take microstrip patch antenna here, source is connected here. Source is connected here. It has some characteristic impedance. This one has some characteristic impedance. I am connecting source here. So there is a impedance match with these two. If it is perfectly matched, the total power is accepted. If there is some deviations or there, some power is reflected. So this is called reflected power. This is called input power. That means reflection coefficient is reflection coefficient, reflected power to the incident power. That is called reflection coefficient. And so if you define that reflection coefficient in terms of decibels, that is called retinal loss in terms of dBs. Now VSWR, it is the reflection coefficient, VSWR, both will give same results, so no need to show same both the figures in the paper, because both will present the same information, because VSWR is equal to 1 plus rho by 1 minus rho. It is completely depends upon rho value. Here rho, the range of VSWR is 1 to infinity. Practical point of view, the acceptable value of VSWR is 1 to 2 only. And if the reflection coefficient retinal loss graph is, if it is below minus 10 dB, then that is the working point of the antenna. In case of, if you see the VSWR, if it is less than 2, that is in between 1 to 2, that is the working point of the antenna. That means there in the reflection coefficient graph, it is less than minus 10 dB. That is same reflected in the, if it is less than 2 dB. That's why both will give same information. No need to show in the papers. We can represent one of the waveform, either VSWR or reflection coefficient. That is enough. No need to show both the waveforms. So here minus 10 dB reference line, and here 2 is the reference line. So below minus 10 dB here below 2, that is in between 1 to 2. The range is 1 to infinity 2. The range is for getting the bandwidth 2 to 1. Yeah. So radiation pattern. So radiation pattern means it is the graphical representation of radiation of an antenna. So simply with respect to spherical coordinates. So spherical coordinates means r, theta, phi. Here, so we have to with respect to theta comma phi. So basically, we can define 3 types of radiation patterns: isotropic, directional, and omnidirectional. So isotropic means, already I said, it is a hypothetical antenna. Isotropic antenna provides isotropic radiation pattern. It is hypothetical antenna or ideal antenna. No antenna in practical point of view will generate equal radiation in all directions. The second one is directional antenna. It produces maximum radiation perpendicular to the axis, particularly azimuthal angles. So isotropic, just imagine isotropic means equally in all directions, just like a cork ball. Now, directional antennas, it produces maximum radiation perpendicular to the axis, particular azimuthal angle. If you take one wire, if you directional pattern, if we apply some voltage to here, it produces electric flux lines around that conductor. If some load is connected is there, some current will generate due to current, some magnetic flux will generate. Already electric flux is there. Now magnetic flux is there. If you imagine what is the shape of the pattern, it is a directional pattern, just like a donut shape. It is a donut shape. Later I will show what is the donut shape. So maximum radiation around this conductor only, because here very small radiation and here very small radiation. Maximum radiation, if you take only wire antenna, if you take different antennas, then automatically radiation pattern will change. So particularly if you take, if you want to see the directional radiation pattern, if you take a single wire, then maximum radiation in this direction only. Now that is omnidirectional. That is I am telling about omnidirectional. Sorry. Second one is directional antenna. Isotropic is all directions. Omnidirectional is only around that conductor, perpendicular to the axis, which is azimuthal angle. Azimuthal angle means this is the x-axis, it is the y-axis, it is the z-axis. Azimuthal angle with respect to x-axis, the maximum radiation around that. That is the omnidirectional. Now coming to second point, directionally is that radiates maximum in particular direction only. So that means suppose this is the horn antenna. This is the horn antenna. It radiating in this direction. Suppose I place it here, one reflector, just like a parabolic reflector. Then it reflects from this conducting plate, the maximum radiation in this direction. This is called directional pattern. That's why horn antenna and high gain antennas are directional antennas, high directional antennas. So that is the meaning of directional antennas. It produces maximum radiation in particular directions only. That is the directional. Now coming to radiation efficiency, already we discussed it in second slide, and the directivity already discussed it. Now, so design of microstrip patch antennas. using HFSS. So far, we have different solvers are there. CST is there, HFS is there, FECO is there, IE3D is there. Different number of solvers are there. Here, HFS is a very powerful tool like CST. Here, the algorithm used in the HFSS is FEM, finite element method. Here in CST, finite frequency integration method, and FICO, they are using method of moments, method of moments technique, they are using numerical method. But in HFSS, what is the algorithm used in HFSS is FEM, finite element method. So if you give the whole system to the HFSS, that solver, first of all, that divides the tetragonal structures, small parts of tetragonal structures. The total large system is divided into smaller parts. Those are called as finite elements, finite element method. The algorithm is applied to each finite element, then combine all the results, it gives the better accurate results. That's why it is using FEM solver. So that's why HFSS is giving more accurate somewhat compared to some other solvers. Yeah, here I can show how it is solving the patches. If you take this is the rectangular patch. If you give into the HFSS, it is divided into a small number of elements, finite elements of tetragonal structures. And here this is the square, and this is the some truncation in the square, and this is the cylinder, small cylinder. This is the larger cylinder. This is the, some arbitrary shapes. So how it is converted, how it is solves the whole structure means first it converted into small parts, tetragonal structures. Apply the algorithm to each small part and combine all the results. That is the algorithm used in the HFSS. That is the finite element method. Now, so most of the people they are telling not only antennas or some other people also. So they are thinking about that is the trial and error method. In antennas, how we are getting the results means trial and error. So many people they are thinking, but actually some standard equations are there to get the desired frequency. So here I am showing Balani's equation to get the rectangular patch. So this is the rectangular patch. You can see here this is the top layer, bottom layer is there, and the substrate is there with the epsilon r value is there, some height is there. So this is the top layer. So in Balani's, if you want to get the particular frequency, suppose if your antenna operating at particular frequency, what are the dimensions of antenna we have to choose? So based on these standard equations, we can get that particular frequency. This is the width of the patch. This is the rectangular patch. This is the length, and this one is width of the patch. That width is equal to C0 by 2FR. Suppose I want to design one antenna at 5 GHz. I want to design antenna at 5 GHz. So FR is resonant frequency is 5 GHz. C0 is velocity of free space or velocity of electromagnetic wave. So width is equal C0 by 2FR square root of 2 by epsilon r plus. What is epsilon r? That is the permittivity of the substrate or relative permittivity of the substrate. A director constant. Where C0 is here, FR is here, epsilon r is here. So now width is easily calculated. Now coming to length. So here the length is related to delta L and epsilon r effective. So what is delta L effective length? If you apply power here, so here feed is there. At the edges, some fringing fields are generating. So due to fringing fields, the length of the patch will change. That is called, this is called as a effective length. So that we have to take the effective length of the patch. That's why L is equal to C0 by 2FR into epsilon r effective 2 delta L. So this is the delta L we have to consider. Then how can you measure delta L? Delta L is equal by H. H is the height of the substrate, and epsilon r effective we can measure it using the epsilon r, and width. Width of the patch is already calculated. H is the height of the substrate. So W by H, this condition should be satisfied. Then E epsilon r effective calculation, delta L by H. Then finally L we can calculate. So these are the W and L are the length and width of the patch only, but not these substrate length and substrate width. So generally the lengths of substrate and are 6 times that L plus 6 into H, where H is the height of the substrate, and here also width plus 6W, that 6H. 6 times of the H we have to consider, then it gives the resonant frequency exactly at FR. Yeah. So from the design here, I have designed one antenna using the equations. FR is defined as 3.8 gigahertz and epsilon R is I have taken 4.4. The height is 0.16 centimeter, that is 1.6 mm. So WP 0.24, LP is 0.18. It is resonating at 3.8. So if you FR, epsilon R, H, if you apply to, these are given to the equations, definitely the WP and LP are 0.24, 0.18 or 0.432 like that, 0.173 like that. Approximately, well, definitely we can get same values. So in Google, so two sites are there, Pasternak is there and EM talk is there. So there, direct equations are there. If you apply directly FR value, epsilon R value, H value, if you want to get 3.8, there, it will show the width of the patch and the length of the patch 0.24. This is in terms of centimeters. That is 24 point something in terms of mm and 17.83 something or 18 point something. Definitely they will get. Then the same values I have used here. That is that the same antenna is designed in HFSS. It is operating at some 3.8 or 3.9, almost all equal. So that's why those are the standard equations. So till now. So if you want to design the antenna at a particular frequency by using those equations, we can design the antenna. Here, the substrate dimensions already told you patch length plus 6 into H and the patch width is equal to patch width plus 6 into height. That is the substrate dimensions. Now, here one key point we have to observe. C is equal to F lambda, lambda is equal to C by F. If you increase the, you can check in the Pasternak and EM talk also. If you increase the frequency, then automatically the width and the length of the patches will decrease because the radiating the wavelength and frequency are inversely proportional. The size, then automatically the frequency of antenna and size of the antenna are inversely proportional. If you want to decrease the antenna size, then the frequency moves towards the right side. Suppose it is 3.8. Suppose if you take this one is as 1, the frequency decreases, then WP and LP may be 40 and this one may be 35 like that. So that the size of the antenna and the frequency of operation are inversely proportional. So by using those equations, we can design the antenna at any frequency. Now, here the challenging task is to reduce the antenna size. We have to operate the antenna at same frequency. That is the challenging task. So that's why simulators came into the technology. That those are HFSS, CST. If they all the equations are available, no need to go for simulators. So for arbitrary structures only, we are using these type of simulators. Now here I want to reduce the antenna size. So previously 6 into height around the size. I want to reduce the here. Antenna 1 is here and antenna 2 is here. Antenna 3, some part is removed here and again some part is removed here. And now here this is the truncated ground. And here two elements are connected, but isolation is very poor. That's why a E-shaped tree-like structure is placed between two antenna elements, and here somewhat isolation poor at the higher frequency. That's why one more strip is connected. This is the MIMO antenna procedure. So antenna 1 to antenna 2. So previously the antenna size will be like this: 6H, 6H, 6H. So I want to reduce the antenna here. You can see here. So 6H, 6H, 6H like that. Now here I remove the remaining part and optimize all the dimensions using simulator. Then finally get the good result. So here you can see antenna 1 is here. You can observe initially the antenna is radiating at 3.9, but here multiple bands are getting. Why are multiple bands are getting means we reduce the substrate dimensions. We are removing the into 6H dimensions are removed. That's why multiple bands are came. Then I have to get the ultra wide band, that is 3.10.6. I have used optimization techniques, all the parameters. This is not a trial and error method. By properly checking the surface currents flowing on the conducting materials conductivity, that is the top layer or bottom layer, we can get the results easy way. So finally, I'm getting 2 to some 13.3 bandwidth. So anytime it is reducing the lower band. Yeah, so this is the isolation, how to increase the isolation. So initially antenna 6, antenna 7 is there. Antenna 6, this is the isolation. So here 3 strips are there. And now next one is one more strip is added here, then isolation. And the third case is here, isolation is improved. Coming to eighth one is that is the red line. So this is the final structure. So finally, I got better isolation. For MIMO system, the acceptable isolation is a minimum 15 dB. Here, most of the band is minus 20 dB above. Yeah. And one more standard equations in the designing the antennas in Balanese is circular patch antennas. This is the A, radius of the circular patch. F, that is the one type of parameter that depends upon the FR, resonating frequency. Similar here also, resonating frequency and epsilon R, permittivity of the substrate. So first you have to calculate the F value, then substitute here, then you can get the A, and then epsilon R, H, and FR we know, then you can calculate it easily here. So here FR is there, I substitute all the values and height and A value. So finally I got the result here, 12 point something. The same procedure I have followed here. So here, this is the decagonal structure here. Antenna 1, then some part of decagonal is removed to get, this is the branch shaped antenna, and the antenna is partially ground. So previously it is the full ground, now it is a partial ground. So generally partial ground gives the wider bandwidth. That is the one of the key point in the antenna design. So, and this one is the truncation, it gives the wider, but this one is also gives wider bandwidth. That's why I have taken partial ground with truncation. And this part is also removed. I got the ultra wide band. Now my work is extended to MIMO technology. So then 2 antennas are placed here, but isolation is very poor here. That's why I have placed one stub is in between 2 antenna elements, so that I got the same bandwidth that is that covers the ultra wide band, and isolation is very high. So here you can see antenna 1 is here, antenna 2 is here. You can see here antenna 1 and antenna 2 and antenna 3 and antenna 4. So finally the antenna 4 is working from 3 to 11 gigahertz. So, coming to isolation, in antenna 3, there is no stub, there is no parasitic element, or there is no stub between the 2 antenna elements. Suppose here I place it. So, we have to optimize all the dimensions. If you place simply stub means then automatically the self impedance here, the self impedance both will change. The the working band of this antenna, the working band of this antenna will change. We have to compromise the impedance bandwidth of antenna 1 and impedance bandwidth of antenna 2, and at the same time we have to increase the isolation. That is a careful study and careful unite the patches and remove some parts and add some patches to the stub. That is very important. So this completely depends upon observation of surface currents flowing on the stub and flowing on surface currents on the ground plane. We have to careful observations is required. So that's why in the antenna 3, the isolation is 15 above. This is the poor isolation. So I have placed one stub between 2 elements. The isolation is less than minus 15 dB. It is acceptable practical point of view. Now, so one more equation. FL, if you want to get the directly ultra wideband or ultra wideband frequency, if you want to get the 4 gigahertz or 5 gigahertz and whatever the frequency. So first of all, to get the wideband. So previously we have taken narrow bands, either rectangular patch equations or circular patch equations that are operating at narrow bands. So that is the full ground. That is full ground. Please remember that is full ground. But here the lower cutoff frequency of basic elliptical shape radiator. You can see this one from IEEE 2008 paper KP Ray. The lower cutoff frequency. Suppose I want to get the antenna operating at 3.1. Suppose I want to design the ultra wideband antenna. The lower cutoff frequency 3.1. So the lower cutoff frequency FL is equal to 7.2 by L plus R plus P plus into K, where L is height of the planar monopole antenna, R is the effective radius, and P is the feed gap, K is the proportionality constant 1.15 per FR for substrate. In terms of gigahertz, this is the standard equation. Suppose I want to get the lower frequency as 5 gigahertz. So we have to adjust these values, you can get the FL value. And suppose I want to get ultra wideband, we have to adjust the L value, R value, P value. This is the constant P, R, and L. Then automatically you can get a 3.1. I will show how we'll get ultra wideband here. So from the basic design, here I am getting this is the waveform. Here A, this is the rectangle, this is the elliptical shape patch antenna. This is the major axis A, and this is the minor axis, and this is the L value. This is the L value. We can see here. L is the height of the planar monopole antenna. This is the L value, that is the B. So 2 times of the B. So 2 into B. So here B L is equal to 2 into B, and A is the semi-major axis. That R is equal to A by 4, and P is equal to cap. It's the cap. All I told you, the partial ground always gives the wider bandwidth. That is the key point. So depending upon this cap and these dimensions, it will give lower frequency. Here I designed FL value is equal to 4.18, and here this is by using similar to the same structure is designed in HFSS. It is I am getting here 3.9 something, approximately equal. 10% tolerance is there. Why I am choosing 4.18, but your intensity is 3.8, 3.1 gigahertz, but here you choose 4.8 means I have a small logic is there. By placing the another antenna, then automatically lower band will decrease. That's why I have chosen 4.8. If I place one more antenna is here, due to reflection from this antenna, the lower band of this antenna will reduce. I have observed many designs I have designed. That's why I have chosen around 4 gigahertz. Yeah. So here antenna 1 is designed, that is operating at 4, and another antenna is designed, another antenna is placed here. Now my intention is MIMO design. So the spacing between 2 elements. I want to reduce the spacing between 2 elements. You can observe here. S is the spacing 4, 5, 6, 7, 8. S11. If you observe the S11, 4, 5, 6, 4 is closer, 5, 6, 7. If 4 is closer means that is the black line that is nearer to the. So previously it is operating at 3.9. If these antennas are closer, the lower band is decreasing to or move to left side. So that means it may be either 3.2 or 3.4. You can see here. If it is moved towards the right side, the lower cutoff frequency is increased. That's why. So previous slide I have said I have chosen 4 gigahertz. And now if the distance is increases, then automatically isolation will improve. If you decrease the element space, isolation is very poor. You can see here S21, 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 4, 5, 6, 7, 8. So it is 4. 4 means that is the pink line. It is closer, it is above the 15 dB. If it is 5 here, and next 6, 7, and 8. So more spacing means less coupling, more isolation. Less spacing means more coupling. More coupling is introduced. So minimum coupling or minimum isolation is 15 dB. So we have to take the small distance and we have to do some work. That is the challenge for us. Then the reviewer will see what is the work done by the author. Then only they will accept the paper. So that we have to take the small value. Here I have choose 4, 5, 6, 7. 4 is the value. Then my work is continued. Antenna 1, antenna 2, antenna 3. And antenna 4, antenna 5, antenna 6, and antenna 7. So initial antenna 1 is there. Truncated ground, already I told you it gives wider bandwidths. And now I place one more antenna is here. So one strip is placed to get the isolation. 2 more strips is added to get the isolation again. Again 2 more strips are added, and again 2 more strips are added.
Hello.
Yeah. Yes, sir. So now you can see here S11 result and S21 results here.
Hello.
Sir.
Sir, your screen is not shared.
Not visible?
No, not visible. No, now okay. Right.
Yeah, now it is okay, sir.
Yes, sir. Right now.
Yeah, you can see here antenna 1, antenna 2, antenna 3, antenna 4, 5, 6, 7. Here you can see if you place antenna 1, antenna 2, this is the truncated ground, this is the 2 element single strip, 3 strips. 5 strips and 7 strips. We can see the final result is it covers the ultra wide band. So 3 to around 15.6. The lower cutoff frequencies. This is due to the reflection from the other antennas or reflections from the parasitic elements. Those are connected between the two elements. So the lower cutoff frequency will reduce, will move to lower band. How it moves means due to reflections, the surface currents flowing on the antennas will disturb so that it increases the electrical path length, then the lower frequency will reduce. Now coming to, we have to check the isolation. Antenna 3, this is the black line isolation. Now one strip is placed here, 2 strips are placed here, 3 strips are placed here, and 4 strips, this is the 3, this is the 5, and this is the 7. So finally, got the better result. The overall isolation is greater than 20 dB. Now we can check the surface current distribution. Here, antenna 1 is connected with the 50 ohm. Antenna 1 is excited, then antenna 2 is affected. You can see easily. So here port 1 is excited, port 2 is also affected. Now here, when I place it here, some part is affected, some part is affected. And here 2, 3 elements are placed somewhat better to previous case. If you place 5, somewhat is a little bit affected, and then it stops the currents from the antenna 1 to antenna 2. The purpose of adding these strips is to stop the surface current from antenna. Yeah, I will conclude 5 minutes. Antenna 1 to antenna 2, after placing all the strips, the antenna 2 is completely free. There is no effect of antenna 1 to antenna 2. That's why I have placed the number of strips between antenna 1 to antenna 2. This is not trial and error. We have to check the again lengths and widths and the position of the patches are also very required. Now we can see here radiation patterns. There is no patches here. This is the radiation pattern. Here, when port 1 is excited due to strips, the radiation pattern will be like this. The shape is also somewhat different with respect to and compared with this one. The second antenna is not affected. Here, the second antenna is affected with so antenna 1. Here there is no affected. Similarly, the port is excited. The port 1 is not excited. Then it is not affected at different frequencies. 1, 2, 3 working band of an antenna. Now similarly. Circular. So you can see the 2008 IEEE paper of KP Ray. Different shapes are there: circular patch equations and elliptical patch equations, triangular, square, and under pentagonal, hexagonal. Different shapes are there based on the equations. So first of all, you have to calculate the lower cutoff frequency. Then we have to extend the what frequency you need. We can do the work. Now. So here the previous similar to the previous, that is the elliptical, this is the circular. Now here my challenge is the spacing is very small. So previously 4 mm I have taken, here I have taken only 2 mm. So same fashion I have designed. So here different T-shaped stuff, slotted T-shaped stuff I have taken. This is the bottom layer, this is the top layer. And now, so here I have introduced a new method, that is added protruded strips to the antenna elements. So due to this, the isolation is very improved. I can show here antenna 2, 3, 4, 5, 1, 2, 3, 4, 5. So by using techniques, this is the ground, this is the top, and next one is slotted, and next one is protruded strips. Finally, got the better performance. It covers the entire ultra wide band. Now, this is the radiation patterns measured. And this is the chamber photos. My antennas in my PhD, my all antennas are tested, measured, fabricated, tested, measured in Hyderabad DRDO, Santosh Nagar. So this is the reflector. This is the anechoic chamber. This is for gain measurement and radiation pattern measurement. So with this one very helpful. And for getting the electrical loss values and VSWR, VNA is sufficient to get the radiation patterns and to get the peak gain values. Anechoic chamber setup is very required. My all works are in PhD. 4 works, 2 papers published in PS and 1 paper is IJCS and 1 paper is this paper is published in AU, International Journal of Electronics Communications. These all works are fabricated, tested, and measured in the DRDO Hyderabad. So if you have any information regarding antennas within my boundary, you can contact my mail ID. You can take my mail ID. You can drop a message to my mail ID or my WhatsApp number. You can contact freely. So now I want to take some rest break. Later, the second session, we will start design of design of uh, design of a 5G sub 6 GHz antenna using HFSS. The next session we will see. So now over to Vishnuvardhan Reddy sir.
Yeah, thank you, sir. Thank you very much for delivering the good lecture on the basics of antenna arrays, introduction to the MIMO antennas, evolution to the 5G, and finally microstrip patch antennas, and also the introduction to the HFSS FEM solver and various antenna design configurations and corresponding results from your research works. It is very good enough for the researchers to continue their research work. And I request all the participants to have a break for 10 minutes, and we'll continue the next session on designing of MIMO antennas for 5G communications.
Yeah, thank you, sir.
Just a second, sir. I request all the participants to turn on their cameras for the group photo session. Please turn on the cameras, all the participants, to have a group photo. I request all the participants to turn on their cameras. Sir, Dr. Tatababu sir, could you please stop sharing your screen? Right. Okay, just a second. Yeah. Right, now the time is around 11:25. We will start at 11:35 after the 10 minutes break. Thank you.